In the second part of Chapter 9, we're going to be looking at predicting some of the specifics associated with the products of SN1, E1, E2, and SN2 mechanisms. So the first thing I want to talk about is going to be our regioselectivity for alkene formation. So this is specifically for our elimination reactions, where we're going to be producing that double bond. And what we mean by regioselectivity is we're going to be talking about where within the molecule that double bond is going to take place. So what we're going to see is that we're going to follow Zaitsev's rule. And it tells us that the major elimination product is the one produced by the deprotonating of the carbon atom initially bound to the fewest of our hydrogens. So what this really means for us is that we're going to produce the most stable alkene through the elimination process. We're going to produce the alkene that has the most R groups associated with it. So we're going to pull off the hydrogen from the carbon atom adjacent to the leaving group carbon atom that already has the fewest hydrogens on it. So to produce the most stable or the most substituted alkene. The one exception to this is going to be those big, strong, bulky bases. If we use those very large, bulky bases, like we looked at with our T-butoxide, that was this big, bulky base. If we use these big, bulky bases, they tend to lead to the anti-Zaitsev's product, meaning to the least stable alkene, and this is just due to sterics. Because the base itself is so large and bulky, it would have a hard time deprotonating a carbon that also has a lot of R groups associated with it. So this is one of the exceptions to Zaitsev's rule if we use these very large, bulky bases. Another thing that we want to look at with these types of reactions is an inter versus an intramolecular reaction. So these are going to be looking at reactions between molecules or looking at reactions within molecules. So remember, intermolecular reactions are going to be reactions between two molecules with different functionality. If we talk about an intramolecular reaction, this is when both functional groups are on the same molecule, so the reaction takes place within one molecule. If we're looking at these intramolecular reactions, they will lead to a cyclization process. Since both functional groups are on the same molecule and the two functional groups react with each other, we see a cyclization happen. It's really through that cyclization that will tell us whether or not we will have an inter versus an intramolecular reaction. Intramolecular reactions will tend to occur over an intermolecular reaction if we form either 5 or 6 membered rings. So remember, 5 and 6 membered rings are our most stable rings. So if we can form a very stable ring, we will see that cyclization happen instead of a reaction between two different molecules. If we have really high concentrations of our reaction species, then we tend to favor the intermolecular reaction over the intramolecular reaction. If we decrease our concentration of our reaction species, then we can favor the intra over the inter. And this just goes back to kinetics. The more we have, the more those particles will interact with each other so that we can see that intermolecular reaction. If we have very low concentrations, it's not very likely that two molecules will come into contact with each other for a reaction, so we will tend to favor that intramolecular reaction. So let's look at an example of what we mean by each one of these. So first off, we're going to look at that intramolecular reaction. So remember, this is the reaction that is occurring within one molecule. So with this, within one molecule, we would have two functional groups. So I have the nucleophile with the O- in this group, or this molecule. I also have the the leaving group, the electrophilic carbon atom, because we have the halide as well. So in an intramolecular reaction, we would see a cyclization happen. The nucleophile is going to attack the electrophile, but they're all within one compound. So if you look at this ring that we're going to be forming a 1, 2, 3, 4, 5, 6 membered ring. With the oxygen as being part of that ring. So since we formed the 6-membered ring, that is what is starting to make this intramolecular reaction very stable for us. We formed a stable ring. So this is an example of an intra-type reaction. If we look at an inter-type reaction, so we'll look at the exact same molecule that we have. So in this scenario, what we're going to be looking at is two of these molecules have to react together in an intermolecular reaction. So I'll take the nucleophilic portion of one molecule, I will have it react with the electrophilic portion of the second molecule. So this is what we have been doing in all of our previous chapters, two molecules together. The only difference is here that molecules are the same. Molecule A and molecule B are identical to each other. We're just taking the nucleophilic portion of one molecule, reacting it with the nucleophilic portion of the second molecule to get us into our final product. The final product for the top one still has the halide. In the bottom portion, we have lost the halide, but it would still have that nucleophilic O-. So this would be an intermolecular type reaction. Two molecules, the nucleophile of one molecule is interacting with the electrophilic portion of the second molecule. No cyclization here. You'll notice we just have one very, very long chain. This would be one very, very long chain if you actually stretched it out and drew it appropriately. But we would have two molecules now joined together. So let's also review that kinetic versus thermodynamic control. So remember, the kinetic is really how we produce the fastest product in our reaction. Thermodynamic control is what's going to lead us to the most stable product that we have. So when we look at these two types of controls, what we're going to be looking at is really equilibrium. Reversible reactions take place under thermodynamic control. So a lot of our equilibrium type reactions fall under thermodynamics. And we drive reactions to completion to make the most stable product. So a lot of these reactions we're going to denote because they're going to have equilibrium arrows associated with them. Irreversible reactions typically take place under kinetic control. No equilibrium is produced. We really have one-directional reactions that are very, very hard to reverse. Most of our SN1, SN2, E1, and E2 mechanisms fall under this irreversibility. They fall under kinetic control, that we're going to just produce the fastest product through that non-equilibrium type condition. So now let's talk a little bit about that kinetic versus thermodynamic control and how we're going to determine them. And we can oftentimes determine whether something will be kinetic or thermo and its reversibility based on the reaction energy diagram. So if we have the free energy of the reaction substantially negative, these tend to be irreversible reactions. So if we look at something along those lines in terms of being irreversible, we have a very exergonic reaction. So if we look at this in terms of the forward reaction, our free energy of activation is fairly small. But if I try to reverse this reaction, you'll notice that the free energy of activation is very, very high for the reverse reaction. So it's very difficult to reverse it. These are ones that we typically put under the context of irreversible reactions. In order to go the other direction, it would require a lot of energy, so it's typically not going to happen. These would be our irreversible reactions. If our delta G of reaction is slightly negative or even positive, these tend to be our reversible reactions. So if what we do is we make our reaction just slightly positive or slightly negative, you'll notice that my free energy of activation to go one direction is very similar. There's not much of a difference to go the other direction. So these tend to be our reversible type processes, or processes that we can reverse. So they tend to be our equilibrium processes. So this would be our slightly negative free energy of reaction. If we have one that is positive, so you can kind of think about these as being our intermediate reactions, our multi-step reactions, you'll notice to go the forward direction is actually a larger free energy of activation than to go in the reverse direction. So these reactions are definitely reversible because it does not require as much energy to go the opposite direction. So those ones that have those equilibrium type reactions, those tend to take place under thermodynamic control. The way we get to the final product, or what stabilizes that final product, is going to be stability, that we finally get to this product that's very low in energy. Where our irreversible reactions, Those don't have to be the most stable products that we're creating. They're going to be the fastest product that we create because we can't reverse them. We can't reverse the process to find a different pathway. So we'll use those energy diagrams that we have been drawing to help us dictate whether something is reversible or irreversible.